speaker, Professor Felipe Pereira from University of Texas at Dallas. He has been focusing his work at multiphase flow in porous media, science computation, and static quantification, etc. So, Professor, you can start. Thank you.
Much for the introduction. First of all, let me thank the organizers for this very kind invitation. On one hand, it's great to have this opportunity to speak for this audience. On the other hand, it's also a wonderful opportunity to meet good and old friends, people I have been working for over 20 years. Now I realize how old I am. But it's really a unique opportunity to have so many friends in just one room. So this is work done at the University of Wyoming. I have just moved to UT, joined with... my focus will be the validation of a model to simulate CO2 storage, CO2 injection in a brine-saturated core. And this involves experiments. The people that have performed experiments and actually built a unique lab are Mohammed Pir, this is the group leader. But Akrabad is one of his postdocs. Dr. Borges from the LNCC spent a year with us. He had an incredible input in the UQ aspects of the problem. We also need a simulator. The main developer at this point is Celestin. And this is a graduate student that has been really doing most of the hard work in this project. He should actually be listed in both columns here, Ahmad Jam. So as I have indicated, we need these two components to be able to look at the validation problem. I will go through briefly discussing methods we have been using for the numerical simulation. And then we need a framework for uncertain quantification. As we'll see, at the core level, CT scans allow us to measure the porosity deterministically. However, we do not know the permeability fields. So there is uncertainty to be quantified and reduced. And then, so I'll go through probably half of my time in items 1 and 2, and then I'll focus on the validation issue. So now to discuss the main ideas of UQ and simulation, let me refer to simple two- and single-phase flows. These are the equations for governing two-phase flows. We have V is the Darcy velocity, lambda is the total mobility, F is the fractional flow function, S is the water saturation. These two coefficients, permeability, absolute permeability, and porosity, are in red because they are the unknowns. So it doesn't matter if you have a beautiful simulator for this problem. If you don't have these coefficients well characterized, there is no hope to make any predictive simulations for these problems. F and lambda are written in terms of KR1 and KR2. These are the relative permeabilities of the fluids, say water and oil. And the typical situation is that you go to the lab and you perform an experiment. Piri is one of the best people in the world to come out to construct these real perms. The situation is not so bad as has been indicated here. They are not worse than a bad lie, and they are really at this point they can be carefully measured. And in our discussion, we take them also as given deterministically. So we do. So the source of uncertainty for us will be through these spatially dependent coefficients. Of course, boundary conditions, initial conditions have to be provided. And this is a tracer flow. The main difference from the previous problem is that as fluid flows, the flow of the tracer does not affect the velocity field. So there is not a coupling between transport and the equation for pressure and velocity. So let me discuss briefly the multi-scale method to discretize the time variable. This is a simpler version of the splitting that Marcel Murad indicated earlier today. So the idea of operator splitting is to decompose large PDE systems describing multiphysics, multi-scale problems. And the original problem is decomposed in smaller systems that describe simple physics. At this point, it can be applicable to compositional and fractured porous media. And the main idea is to say if we want to decompose just the pressure saturation problem, given a state of the system, say the saturation at some point in time, we update the velocity field, and then with the new velocity field, we take transport, we update the saturation variable, and as we perform these two steps, we naturally take different time steps respecting physically or mathematical constraints. So this is the basic idea. And it allows us to use distinct numerical method for distinct PDEs, and moreover, as I have indicated, for computational efficiency, distinct time steps for distinct physical processes. In our combination of methods consists of high-resolution central schemes for hyperbolic systems. I wish to emphasize the issue of parallelization. In the UQ discussion that we are aiming at, we end up solving thousands of simulation problems. So being able to run them in parallel is essential. We have also taken advantage of clusters with CPU and GPUs. And for elliptic and parabolic problems, we use mixed finite elements. So the current code that I will refer to is using Trilinus for our linear algebra problems. Work with Dr. Garcia from the LNCC, we have identified that it does not scale well for a very large number of processors. If you have more than, say, 16 or 32, you start to see a degradation in the speed up. So for this reason, we have been looking at multi-scale methods to improve and be able to use efficiently a larger number of processors. But in any way, this type of methods for two-phase flows was developed jointly with Fred a long time ago. Later, Dr. Abreu extended it to three-phase flows, and currently we have it fully implemented for compositional CO2 brine systems. So the scheme we have been looking at for an elliptic equation refers to three scales. The small scale is the fine grid where we aim at discretizing our problem. Capital H refers, say, to the size of subdomains. So typically what we have in mind is that each one of these big age blocks will be attached to a different processor. And moreover, we introduce an intermediate scale H bar where we impose continuity of the flux and normal component of continuity of normal component of flux and pressure. So with this framework, we have developed an iterative or a direct domain decomposition procedure that allow us to solve the problem using multiple processors or multiple GPUs. And so some remarks about the method is that the conservation of the flux, after we are done with this iterative procedure or with this direct procedure where we glue together multi-scale-based functions until we reach the domain size, after we are done with this step, we have flux conservation only in this H-bar scale, and then we have to add a downscaling step to recover conservation in the smallest scale. So all this is done in 3D, except for the downscale, that we are still debating the best way to perform such a procedure in 3D and in parallel for multi-phase flow problem. If it's single phase, it's not a problem. So the point here is that these multi-scale based functions are completely local. So in this sense, the problem is naturally parallelizable in CPU-GPU machines. They typically are not very large. You can solve several of these problems in GPUs. And the method has two extreme cases that I wish to mention. If we make the intermediate scale equal to the mesh size, defined mesh size, then we recover a simple direct fine grid solution. So this is a good tool to debug the code. And if we assume that h bar is equal to the subdomain size, so we are close to some upscaling techniques of use in reservoir engineering. So the method can be used as an alternative to upscaling if we consider some h bar smaller than capital H. So you get a better resolution, and you don't go directly to the coarsest discretization that would be close to a typical upscaling. So this is a picture I have shown for a while, indicating on the left a direct fine grid simulation, on the right the result of using this Moon procedure. So they compare, I think, very well. This appeared in the PhD thesis of Rigelo, and this is the procedure that's currently almost done, fully implemented in 3D. Okay, so let me now discuss the uncertainty quantification framework that we need to look at the validation problem. And the context that I will start and I refer to at this point is that I'm aiming at characterization of porosity and permeability at the lab scale. We wish to produce predictions at the field scale, and in this context, we assume that we know the system of PDEs in the Darcy scale, and we have some type of dynamic data that will allow us to estimate porosity and permeability fields. Okay, so this is the context. And the type of dynamic data that we typically have are production curves. So suppose we are looking at two-phase flow. Initially, you start to pump water in the reservoir, and in a production well, you see for a while 100% of oil produced, and at the breakthrough time, you start to produce a combination of oil and water. Okay? So in sparse locations, we have a lot of information, because for almost all times, we will have a point through this curve. And this is the available data that we have to reduce uncertainty in the characterization of these spatially dependent coefficients. But at the bottom line is that we wish to sample permeability and porosity fields conditioned on this production data. So let me refer to this as the probability of Psi is the pair permeability and porosity conditioned on these measurements. And through Bayes' theorem, the posterior distribution is proportional to a prior multiplied by the likelihood function. Okay, so we assume this form we follow the literature in this area, we assume this form for the likelihood. And in order to be able to use this for practical purposes, we have to somehow specify the prior distribution that should contain static information. For example, if we know the permeability and porosity at a few locations where we have wells, this is the type of information that should be also built in the prior. And unfortunately, this is an ill-posed inverse problem, right? There are several distributions of permeability and porosity that will end up leading us to the same very close, very similar production curves. So the way we look at this problem is that we should identify a family of permeability and porosity fields that are consistent with the available dynamic data, and then we run simple Monte Carlo to make predictions of the future. Okay, so the UQ framework has two steps. In the first step, we use dynamic data to reduce uncertainty and determine an ensemble. And in the second step, once we have the ensemble, we run MC forwarding time to make predictions. Okay, so this is the type of framework we are working with. So typically in the literature, you find that one of these parameters is somehow random, and there is an ad hoc or either stochastic or deterministic relation between them. So the framework I'm describing does not require that we specify a priori a relation between these properties. So we eventually, and this is what we will use in the lab scale, we assume that they have the same correlation structure, however, they are statistically independent fields. If there is a correlation between permeability and porosity, it's something that the framework should give us. This is not something that we wish to impose, because there are no, as far as I know, there are not universal, there's some physical law that would relate them so the relation is rock dependent. So concerning the prior, we will use Gaussian fields to represent permeability and porosity that are specified by the 2-point correlation function, say mean 0. In our experiments that I'm about to show, I'm assuming this quadratic exponential for the 2-point correlation function. L is the correlation length. And so we assume K to be log normal. And this is a simple mapping of the Gaussian field to the 0-1 interval such that we can model porosity. So there are several headaches associated with this characterization step in this framework. So typically, permeability fields are defined in very fine meshes, and so we would have to populate a huge number of mesh blocks, and the direct sampling is related to very large dimensional space. So a typical step in this framework is to use the KLE expansion to parameterize the uncertainty. So the idea, I have to run, is to write the Gaussian field in terms of a finite sum where lambda and psi are respectively eigenvalues and eigenvectors of the covariance operator, and the theta is a family of normal 0-1 random variables. And this cutoff number, n, is related to the decay of the eigenvalues. So depending on the covariance structure, we have to determine the proper n here. And in order to sample from the posterior, the idea is to construct a Markov chain such that the posterior is equilibrium distribution of such chain. This is the algorithm. This is the classical Metropolis-Hastings algorithm. And the point is that in one step of the algorithm, we have to compute the likelihood function. So I don't want to go through the whole thing. And this is a very expensive step because we have to go to our problem of interest, in define mesh, run the forward simulation, and then decide if a sample produced by this instrumental distribution Q will or will not be accepted. Okay, so typically for porous media flow applications, you see at this point 8-9% of acceptance. So you run 10 forward expensive simulations before you can make a choice. So in the process, the parallelization is not a trivial issue. So the acceptance rates are small, and parallelization is not as simple. So there are different ways to proceed. We have looked recently at a prefetch strategy that allows us to use multiple GPUs to be able to travel in the chain using larger steps than one step at a time. And there are very nice two-stage procedures where in the first stage we run a surrogate model, typically an upscale model, and then if this sample is approved, say in this first stage, then we move forward to the next fine level solution. So the idea was originally introduced in 2005 by Christian and Fox, and Mailybaev and collaborators wrote two very nice papers where they discussed the application of these methods to porous media flows. We have worked a little bit in this direction on adding variability in porosity to the problem, and also use it to characterize fractured porous medium. And more recently, we came up with the concept of the multiphysics in Monte Carlo, where we aim at using typical engineering techniques such as huff-puff, tracer injection, as filters in a multi-stage procedure such that we reduce as much as possible fine-grid expensive simulations. So this is what we refer to as these multi-stage multiphysics procedures. And so let me give you a few results to indicate how this type of methods work together, the simulation strategy plus UQ. So this is a noise recovery problem. I have data at two locations, a corner and a center well. This is the typical profile that we see as we inject water on the bottom left, produce oil top and corner and center wells. You see, so if I use, in this case, single physics, 3 stages, if I use just a plain Metropolis-Hastings algorithm, we get acceptance of 9%. And then by adding 2 considerably less expensive, from the computation point of view, steps, then we can bring the acceptance rate up to 43%. And if we combine a tracer injection with the 2-phase problem, we can, with very inexpensive, you see, if we aim at a 128 by 128 2-phase flow problem, if we run 2 very inexpensive filters, we can bring the acceptance rate up to 32%. So these are techniques that we have been used to speed up the original Metropolis-Hastings algorithm. And these are some indications. So this is some indication that we can predict. Okay. So the vertical line here refers to the fraction of the production curve that we use for characterization. So we use this information to select an ensemble of acceptable permeability and porosity fields. And after I have these fields, I run the forwarding time simulations. So red, in this case, I have synthetic case where I know the answer, and then I compare the predictions for single and two-stage procedures. Okay? And they perform very well with a relatively small number of forwarding time simulations. So with an ensemble of 1,000, we can get a pretty good prediction. Okay? So these are the two, say, methodologies that we combine to look at the lab scale problem. So the context now is that we are looking at CO2 being injected at the top of a core in a drainage experiment. So the core is initially saturated with brine. We aim at characterization at the RV scale. So this problem, it's a fully 3D problem. It's a 1D attempt to simulate this problem fails completely because we see fingering going on here. And the goal is to make prediction at the core scale. So we don't have production curves here. What we have are CT scans. For a family of times, we have the CT scan will produce saturation values along these slices. So our idea is to use the first measurements of the scan to be our dynamic data, and then from this we select permeability fields. As I mentioned, porosity is known in this context, and with these permeability fields we try to predict the fluid flow at later times in the experiment. Okay, so these are the main ideas. We are not alone in this attempt. There are 2 groups looking at this that have looked at this recently. The agreement they get between simulation and experiments is essentially qualitative, and we are aiming at a more quantitative type of agreement. So we are looking at a 2-phase, actually 3-component compositional model in the drainage. As I mentioned, we know the real perms. We know the porous, permeability is the unknown in the case. We assume that they share the same correlation structure, but not the strength. So S is also to be determined by the data, the strength of the permeability field. We have attempted single and two-phase procedures, and dynamic data comes from core measurements. So the composition simulator has been adapted to run the core geometry. So this is precisely, this is our reference. So I'll test the methodology for a synthetic case where I know the answer, and then I'll apply it to the real lab experiment. Okay, and so this is our reference run. And so this is the result of on the right is the ensemble average of the saturation fields that were accepted corresponding to the accepted permeability fields. So this is a reference saturation profile for several of these slices, 4 of these slices along the core, and on the right is the ensemble average of the accepted saturation profile. So, of course, there is not uniqueness, but they do seem to refer to the same piece of rock. And this is a more quantitative description of the same picture. So we are looking at how the ensemble average, so in the chain, the initial one was the blue, so it gets deformed and getting closer and closer to the experimental or the reference run, which is the red, and then the ensemble of the accepted fields produce this profile. So they coincide pretty well. So this is the characterization step, and then we have several indications that the procedure works well. For example, this is an indication that the strength of the permeability field converges to the one that we set. We know this value. We start with 0.5, and as we move through the accepted MCMC realizations, the strength converges to the right number. These are some accepted fields. The one on the left is the reference one, and these are 2 of the fields that we accepted. The size here should be the same. Ahmad, you have to explain this to me. But you see, they are not identical, but they're pretty close to each other. So these are 2 of the accepted fields. And this is, here we have checked that also we recover the correct absolute permeability. So the red line is the absolute permeability measured for a single phase flow for the reference run. And this is how the chain, for different initial conditions, how the chain goes towards the correct absolute value. Okay, so we have looked at the problem from different points of view, and now they all indicate a very nice convergence to the reference run. And once we have selected a family of accepted permeability fields, we run the forward problem in time, and this is what we get for ensemble average versus reference. Again, you see the main dominant fingers are well captured, and this is a quantitative statement of prediction. So we do have a very nice reference agreement between the reference simulation and the ensemble average. Okay, so this is, I have 1 minute. So this is our goal. Our goal is to validate the problem in this sense, right? The first measurement of the CT scan is used as dynamical data, and then we predict the last one. So typically, the first one is made after 15 cc of CO2 is injected, and after about 66 cc's, they make the final measurement. So our aim is to make sure that the composition will be able to predict this final profile in this ensemble average sense. So let's look at the real data. So this is the lab where these experiments were performed. It's a unique lab. They have adapted a hospital CT scan. They put it in horizontal position. It's a 2-floor lab. So they prepare the sample on the first floor, and then they go through the floor, the ceiling, and then the sample goes through the scanner, and they record the saturation, porous, etc. So this is the data. So light blue indicates the CO2 that's being injected at the top. As CO2 enters, you see that a 1D simulation has no chance to describe what's going on here. These red spots are just, this is a point where they have equipment to measure pressure values. So these are slides that we have to ignore in our analysis. Otherwise, this is the data that we use for saturation at slices. So this is the validation. We have the experimental result, the experimental average saturation values at 15 cc in red, and the black curve is the ensemble average of our accepted saturation profiles. So except for this bump here that might be related to one of those, I forget the name, the equipment to measure pressure they have at this location is introducing a bad behavior for the experiments, for the measurement here. Otherwise, we get a nice agreement. And then we predict, at the end of the experiment, we make, this is the prediction. Okay, so again, except for this bumpy area, I think the agreement is pretty nice. So this is what we understand for a quantitative model validation for the injection of CO2. So we have two different projects aiming at different aspects of model validation. This group has a lot of pore scale network models running for 2- and 3-phase flows. We are aiming at trying to validate the continued description of 2- and 3-phase flows against these pore scale models, and also against direct numeric simulation at the pore scale. So thank you for your attention, and I'll be happy to take questions.
Thank you, Professor.